students, today we will study electron concentration in intrinsic semiconductors. We know that when the temperature is greater than 0 degree kelvins, means at room temperatures the electrons move from valence band to the conduction band. The electrons are present in the conduction band, leave behind holes in the valence band. As we saw earlier, when the temperature is greater than 0 degree Kelvin, semiconductor become conducting and the large number of electrons are present in the conduction band and holes are seen in the valence band. Now we will find out the number of electrons in the conduction band. It means that the electron concentration in intrinsic semiconductors. So we should know this formula to finding out the number of electrons in the conduction band. So the formula is n equal to integral from EC, that is bottom of the conduction band, to the top of the conduction band. This is Fe, that is Fermi energy function, and GCE, density of state, D. Suppose this is equation number 1. So equation number 1 can be used to find out the concentration of intrinsic semiconductors. So in other words, this Fermi function denotes the probability of occupancy of electrons in the conduction band, and this GC is the available energy states per unit volume, that is density of states in the energy range E to E plus D. And the Fermi function, according to Fermi-Dirac statistics, FD statistics, the Fermi function can be given by Fe is equal to 1 upon 1 plus exponential of E minus EF by kT, where EF is Fermi energy, K is Boltzmann constant, and T is temperature. And also the density of states, that is GCE in the conduction band, is given by this famous formula, that is GCE is equal to 4 pi h cube in 2me to the power 3 by 2 E minus EC to the power half. This is under root E minus EC for E is greater than EC, when E is greater than EC. Suppose this is equation number 1. So this is the formula for Fermi energy function, this is equation number 2, and this is the formula or expression for density of states, GC. Then we will put the value of GC and Fe from equation number 2 and equation number 3 into equation number 1. Okay, so after substituting above values of Fe and GC in equation number 1, so equation number 1 becomes, that is the number of electrons, that is concentration of electrons in conduction band, equal to integral from EC to infinity. Why infinity? Because the lower level of conduction band EC and there are infinite energy levels above EC, hence we set the limit of integral from EC to infinity, 1 upon 1 plus exponential of E minus EF by kT into 4 pi h cube 2me power 3 by 2 E minus EC power half. So after putting this into equation number 1, means this integral become like this. Now we will take this term to the denominator. Okay, this is also this is already a denominator. We will rearrange this term and this equation will become, after rearranging, I have brought this term into the denominator of this, and these are the constant values, 4 pi h cube and 2 me to the power 3 by 2. This me is effective mass of the electron. Okay, so me is the effective mass of the electron, and this EC is the energy of bottom of the conduction band. This EF is Fermi energy, H is Planck's constant, K is Boltzmann constant, which has value of 1.38 into 10 to the power minus 23 joule per Kelvin, and this T is the temperature. Okay, now so when number of electrons is very small than the available energy state, so we apply one condition. When number of electrons is very small than available energy states, it means that E minus EF is very greater than KT. This E minus EF is very greater than KT. It means that when power is E minus EF is very greater than KT, then this power of exponential is very greater than 1. It means E exponential to the power e minus ef by kt is very greater than 1, so we can neglect this 1 in this denominator. We can neglect this 1, so 1 plus e to the power e minus ef by kt is approximately equal to e to the power e minus ef by, that is exponential to the power e minus ef by kt. Since this power of exponential power is very greater than 1, so by approximating this value, okay, we will put this into the equation number 4. So equation number 4 implies now n is equal to integral from ec to infinity 4 pi h cube 2 me, that is effective mass of electron, to the power 3 by 2 e minus ec power half. Okay, here we have neglected 1, so the in denominator the term will remain e to, this means exponential to the power e minus ef by kt. Now this e exponential to the power e minus ef by kt, it is in denominator, so we will shift it to the numerator, so it will become e exponential to the power minus e minus ef by kt. So we have shifted this term to the numerator, so the power will be negative e to the power minus e minus ef by kt. Now this term is a constant term for pi h cube 2 me to the power 3 by 2, so this term can be taken outside outside the integral, so we have taken this term outside the integral. So inside the integral the terms are remain e minus ec to the power half e to the power, that is exponential to the power minus e minus ef by kt into d. Now we will introduce the term to the in the power of exponential, that is ec, so we can adjust ec in this power of exponential. Okay, power in this numerator, that is power of exponential. So in this term we have adjusted ec minus ec and plus ec, since minus ec and plus ec, okay, that can be cancelled out. So so we can adjust ec here, minus ec plus ec. Now we will bring this ec nearby e and this ef to the end, so we will get in this term, so we will rearrange this terms in the power of exponential, so we will get, so 4 pi h cube 2 m 3 by 2 as it is, integral from ec to infinity e minus ec power half e to the power this, I have brought this ec nearby e, so e minus ec, since here is e minus ec, so I want here e minus ec, so that's why I have brought ec here, e minus ec plus ec, okay, minus ef, so I brought this ef here at the last, so ec minus ef. Now we will solve this exponential, so this is e minus ec plus ec minus ef divided by kt, so this minus is with all these terms, so we'll break out this minus, so this minus with this e minus ec, this minus is also with ec minus ef, so this minus we can multiply inside, so we will get here minus e minus ec and here minus ec minus ef by kt. Now we'll focus to solve this exponential only. So we know that by the rule of exponential, e to the power a plus b can be written at e to the power a into e to the power b. So suppose this is a and this is b, okay, and kt is common with all this term, so we can separate this kt is the common denominator, so we can separate it, so e to the power minus all terms are as it is, so e to the power minus e minus ec by kt minus ec minus ef by kt into d. Okay, now it is in the form of that e to the power a minus b, so e to the power a minus b can be written as e to the power a into e to the power minus b. So we will split this exponential, okay, we will split this exponential, so we will get here all terms are as it is, e to the power minus e minus ec by kt into e to the power minus ec minus ef divided by kt into t. So we will bring this term outside the integral in front, Okay, and inside we kept these two terms inside the integral, and we will bring this term outside the integral in front. So we will get n equal to, that is concentration of electrons in conduction band, equal to 4 pi h cube twice me to the power 3 by 2 into we have brought this term outside the integral, e to the power minus ec minus ef by kt. So integral from ec to infinity, e minus ec half e to the power minus e minus ec by kt d. So this e minus ec is here and e minus ec. Now this integral can be solvable. Okay, now in next slide, so we will take this minus inside. So the this numerator, the power of exponential become ef minus ec. So we will multiply minus inside this bracket. We will open this bracket. So we will get 4 pi h cube twice me to the power 3 by 2 into e to the power, that is exponential of e f minus ec by kt. Now we will solve this integral. Okay, so suppose this is equation number 5 and we will solve this integral. So this integral of the type of this, so the above integral of the type integral from ec to infinity x to the power half into e to the power minus ax dx. Okay, so this integral of this type. Okay, so x is nothing but e minus ec, and mine a is 1 by kt, and x is e minus ec. Okay, so this integral is of this type of standard integral, and we know the solution of this integral, this type of integral is this, where x is equal to e minus ec here and a is equal to 1 by kt. So the solution of this integral, we know the solution of this integral is nothing but under root pi divided by twice a into root a. Okay, so we will put this value in the solution of this integral, where x is equal to e minus ec and a is equal to 1 by kt. Okay, so in place of this integral, okay, we will put this solution. So equation number 5 becomes, okay, 4 pi h cube twice me to the power 3 by 2 into e to the power ef minus ec by kt, and we have put the solution under root pi 2 into a is 1 by kt, into under root a, that is 1 by kt. So we will solve this now, this term. So this 1 by kt is the power half, and here 1 by kt is power 1. So this 1 by kt is power half, and this 1 by kt is power 1. So 1 by kt is power 3 by 2. So it will become 1 by kt power 3 by 2. When we will bring into this term to the numerator, so it will be kt to the power 3 by 2. So it will be kt to the power 3 by 2. When it will become, it will go to the numerator, so it will become reverse, kt to the power 3 by 2. Now this is 2 pi 2 me to the power 3 by 2, and here is kt 3 by 2. So we can put kt inside this bracket, 2 me kt 3 by 2. So this kt can be put here in the bracket, because same powers are there according to the mathematics, rule of mathematics. So 2 me kt to the power 3 by 2. Okay, now here's pi, this is pi to the power 1, and this is pi to the power half, this is root pi. So root pi into pi, it is nothing but pi 3 by 2. So this pi can also be taken here in the bracket, and we can, this 2 ones are 2, 2 twos are 4, so 2 will be there, 2 pi. Okay, now I am taking pi inside this power, because this pi and root pi is nothing but pi to the power 3 by 2. So pi can be brought here inside the bracket. So inside the bracket, the term will be 2 pi me kt to the power 3 by 2. Okay, now this is h cube. So h cube can be written in terms of the power 3 by 2 in this way, h square to the power 3 by 2. Since 2 can be cancelled out, so again we will get h cube. So h cube can be written as h square to the power 3 by 2. So again, this is the term related to the power 3 by 2. So we will bring here. So in this bracket, we'll get 2 pi me kt h square to the whole power 3 by 2, and here is the term e to the power ef minus ec divided by kt. Now this term 2 into this bracket is denoted by Nc. Okay, so concentration of electrons in the conduction band is equal to Nc into exponential to the power EF minus EC by kT, and this bracket term, that is Nc, is nothing but known as effective density of state of electrons, where Nc is equal to 2 into 2 pi me kT upon a square to the whole power 3 by 2. So this is the effective density of states of conduction band for electrons. So this is the final expression of the electron concentration or number of electrons in the conduction band of intrinsic semiconductor. The value of effective density of state, okay, for silicon at room temperature is 2.8 into 10 to the power 25 per meter cube. Okay, so today that's all. We have found out the electron concentration in conduction band of intrinsic semiconductors and expression related to it, and we have seen the complete derivation related to it. Thank you very much.